millions of distinct half-moon shapes are being carved into the surface of the Sahara Desert. This massive effort is part of a land restoration initiative costing over $1 billion. One can notice how the excavated lines stretch across the horizon. But this is just the beginning. Why use this specific geometric form for digging? The work continues quietly under the sun. At first glance, they look like ordinary pits, but in reality, they trigger a mechanism to revive the ecosystem. These structures turn millions of acres of barren sand into green, fertile areas. This process acts as the key to stopping the spread of desertification. It does not end at this stage. The soil is now ready to support the next cycle of growth. 9,200,000 square kilometers covers the surface of the Sahara Desert, an area roughly equivalent to the size of the United States. This massive geological formation occupies nearly 1/3 of the African continent. Why is this arid zone expanding with such alarming speed? To the observer, the dunes appear static and unchanging. However, compared to the early 20th century, the desert has increased its territory by 10 to nearly 20%. And this is not the limit. The expansion relentlessly pushes south into the Sahel belt. This semi-arid strip spans across more than 20 African nations, where hundreds of millions of people rely directly on the land for survival. At first glance, the region seems plagued by absolute dryness, but in reality, the Sahel experiences short yet intense rainy seasons every year. The paradox lies not in the absence of water, but in the ground's refusal to accept it. Severe degradation has transformed the physical properties of the soil surface. It hardens into a water-repellent crust that prevents rainwater from soaking into the depths. One can notice how heavy torrents strike the ground and immediately form rapid streams, causing flash floods before disappearing. The water runs off the surface instead of nourishing it. This creates a dangerous, vicious cycle where drought destroys the soil structure and subsequent rains wash away the remnants. Erosion accelerates, stripping the land of its ability to retain moisture. But the response to this crisis is gaining momentum. A solution emerged in 2007 under the banner of the African Union. The Great Green Wall Initiative stretches approximately 8,000 kilometers from the Atlantic coast in the west to the Red Sea in the east. It involves coordination between more than 20 countries attempting to halt the sand. However, the project is not a literal continuous wall of trees as often imagined. It functions as a complex mosaic network of ecosystem restoration, where solutions are tailored to local soil conditions and water availability. The goal is to reshape the interaction between water, land, and people. It gets more complex further on. This strategy corrects the fatal errors of previous decades. Billions of saplings were once introduced into the region, supported by billions of dollars in international aid. Yet 80 to 90% of these young trees died after just 1 or 2 rainy seasons. One can see why the approach failed. The saplings were planted in soil that had lost its structure and was devoid of living microorganisms. The sun scorched the surface and moisture evaporated within hours. Planting life into dead soil proved as futile as installing a sophisticated machine on a collapsed foundation. The true challenge is not a lack of trees, but the restoration of the land's capacity to sustain life. Thousands of hectares across the Sahel are subject to a strategic transformation. The Great Green Wall focuses on restoring degraded land by improving how water and soil function, rather than simply planting trees. One can notice how the landscape changes under this approach. But this is just the beginning. Why are local techniques applied here? The ecosystem requires specific interventions to survive. These methods effectively slow runoff, reduce erosion, and bring life back to farmland and ecosystems. At first glance, the manual labor seems simple, but in reality, at the core of these efforts is one crucial technique. Workers are digging half-moon pits to capture rainwater. It is visible how the curved depressions hold moisture to revive the soil. The land is now prepared for the next stage of recovery. Short, violent bursts characterize the rainfall in the Sahel, where water does not fall gently, but arrives with aggressive force. It rushes downslope at high speed, threatening to wash away the top layer of earth. A straight trench would simply channel this runoff away, but the curved, open-ended shape intercepts the flow from multiple angles. This forces the water to slow, spread, and settle before it can escape. The crescent form naturally reduces water velocity without trapping it completely, allowing gradual infiltration instead of overflow. Why do engineers rely on this specific geometry? A straight trench seems easier to construct, but without the curvature, the structure would fail to maximize the absorption of the sudden deluge, rendering the excavation futile. This design works with gravity and terrain rather than against them, ensuring the half-moon pit succeeds where other structures fail. Excavation follows a clear and deliberate technical process, starting with the terrain analysis. Contour lines on the slope are identified using ropes, stakes, and simple hand tools. This ensures that the pits are positioned perpendicular to the direction of runoff during heavy rain. One can notice how the crescent shape opens uphill to catch the incoming torrent. The back of the pit sits on the lower side to firmly hold the water in place. A typical pit measures about 4 to 6 meters in diameter. However, the depression is only 20 to 40 centimeters deep, with an outer earth bund rising 25 to 50 centimeters high. It gets more complex further on. The pits are not dug deep because the goal is not to store water like a pond, but to slow runoff long enough for it to infiltrate the soil. Roughly 8 to 15 meters separate the units, aligned in parallel rows along the contour. The camera glides along the slope, revealing a stepped hydraulic system formed by the earthworks. The entire process requires only hose, shovels, and manual labor. On average, one person can complete a single pit in about an hour, making the method low-cost and highly scalable. But this is just the beginning. Farmers spread seeds of native grasses such as andropogon or centrus inside the hollows after digging. These grasses are highly drought-resistant and develop deep, fibrous root systems. At first glance, scattering seeds looks simple, but in reality, the roots help stabilize the soil and improve infiltration significantly. Once established, the plants trap organic matter and moisture, creating the first living layer that allows the soil to recover. In practice, the impact of half-moon pits becomes clearly visible after 2 to 5 years. What initially starts as small patches of grass gradually expands into continuous ground cover. Vegetation density increases season after season. And this is not the limit. Studies in field results in Niger, Burkina Faso, and Senegal show that restored areas can reach 40 to 60% vegetation cover, compared to near zero before intervention. Improved soil moisture and structure allow shrubs and native trees to regenerate naturally. One can observe how the process reconnects fragmented habitats over time. Insects, small animals, and grazing systems return, turning isolated green patches into functioning ecosystems rather than temporary vegetation islands. Beyond ecological recovery, the half-moon pit approach also creates livelihoods. As soil fertility improves, many communities are able to grow crops such as millet and maize again. This provides food, income, and seasonal employment through land preparation, maintenance, and harvesting. The results of this method are remarkably strong despite its extremely low cost. Local communities can dig the pits by hand, maintain them themselves, and gradually expand the system over time. Tree planting is a direct intervention, while half-moon pits act as a system trigger. In the harsh conditions of the Sahel, it is this system-based approach that delivers results that are fast, durable, and scalable. Field projects in Niger and Burkina Faso show that restored land can increase millet and maize yields by 50 to 100%. This brings thousands of hectares back into production, concluding the cycle with food security and household income for entire communities. Millions of liters of fresh water lie hidden just beneath the dry surface of African riverbeds. Following half-moon pits, another widely used restoration method appears across the continent, the sand dam. This technique involves building a low concrete or stone wall across seasonal riverbeds. But this is just the beginning. One can notice how the structure traps sand carried by flash floods. Why store water inside the sediment? To the eye, filling a dam with dirt seems counterintuitive. However, this forms a natural underground reservoir capable of storing liquid within the sand itself. At first glance, open water seems preferable, but in reality, up to 90% of it is lost to evaporation in these regions. Sand dams largely avoid this problem by keeping the water underground. This protects the resource from the sun's intensity. The process is only gaining momentum. Communities access the water through shallow wells to support livestock during long dry seasons. Therefore, more than 1,000 dams now exist in Kenya, alongside projects in Ethiopia, Tanzania, and Zimbabwe. Field studies show these structures triple local water availability and significantly increase agricultural output. They also reduce erosion effectively. Today, this remains a reliable and scalable solution for drylands. 30 to 80% is the increase in crop yields achieved by the stone line technique. Also known as stone bunds or contour stone lines, this method serves as a vital tool in the Great Green Wall initiative. Workers place rows of loose stones along contour lines on gently sloping land to interrupt surface runoff. One can notice how the barriers stretch across the terrain, waiting for the rain. But this is just the beginning. Why do farmers construct these heavy barriers across the dry fields? At first glance, it seems like a simple border, but in reality, it is a calculated system to control water flow. The stones slow down seasonal floodwaters, forcing sediments and organic matter to settle instead of washing away. Fine soil accumulates behind the wall, gradually rebuilding fertile topsoil where crops can grow. The lines also increase water infiltration, recharging soil moisture without blocking the flow completely. It is visible how the earth absorbs the liquid instead of losing it to erosion. This technique has been widely applied in Burkina Faso, Niger, Mali, and Ethiopia. The process is only gaining momentum. Farming areas with degraded soils see the most significant benefits. Field results show that millet and sorghum thrive thanks to this retention of water and nutrients. The method requires only local stone and manual labor to implement. One can notice the contrast of green vegetation growing against the stone rows. Because they are durable and low cost, stone lines remain effective for decades. They form a long-term backbone for dryland restoration systems. Thus, the land stabilizes for future planting. 80 days a year was the duration residence of the capital spent wearing masks during the 1990s to escape the fine dust. Why did the skies over Beijing turn from day into night with such alarming frequency? The answer lies thousands of kilometers away. Monsoon winds regularly swept massive sandstorms down from the Gobi and Taklamakan deserts, burying the city in suffocating clouds that blocked out the sun. The air turned a thick, hazy orange, forcing millions of citizens to filter their breathing to avoid inhaling the grit blowing from the wasteland. Because of tectonic shifts that occurred millions of years ago, the Taklamakan Desert was carved into the earth. The massive uplift of the Tian Shan Mountains to the north and the Kunlun Mountains to the south created an impenetrable barrier against the elements. These colossal ranges blocked nearly all moisture traveling from the Indian Ocean and Siberia, turning the basin between them into a vast arid trap. One can notice how the dry heat dominates the landscape, where average rainfall drops below 100 millimeters per year. But this figure is almost 10 times lower than the precipitation levels in California, a region already known for its intense aridity. To put that in perspective, every square meter of land here receives only the equivalent of a single 500 milliliter bottle of water per week. Far too little for ordinary vegetation to survive the scorching sun. Faced with this geological reality, the government launched the 3 North Shelter Belt program in 1978. One can see that the project functions not as a single line of trees, but as a vast network of thousands of forests. It comprises windbreak belts and ecological lakes stretching more than 4,500 kilometers from the Xinjiang Autonomous Region to Heilongjiang Province. The ultimate goal is to plant 35 million hectares of new forest by the year 2050 to permanently halt the advancing sand. This effort has already raised the country's forest coverage from just 10% in 1949 to over 25% today. But this is just the beginning of the logistical challenge. Chinese engineers survey the terrain using satellite mapping and drones to analyze dune movement and wind direction before a single person steps onto the sand. Based on these data, they design a massive grid system to stabilize the shifting ground. It is visible how trucks transport millions of pounds of straw hundreds of miles into the heart of the desert, navigating terrain where paved roads do not exist. Heavy vehicles often sink into the soft sand, requiring immense effort to free them and continue the supply chain. Once on site, teams of workers dig shallow trenches and place bundles of straw into precise grid lines measuring 20 by 20 feet. They lay the material diagonally across the dunes to maximize wind resistance. Although the work looks simple, it continues through the relentless sun, with temperatures rising above 49 degrees Celsius. Because the woven pattern stabilizes the shifting dunes, it creates microzones where moisture can linger long enough for planting to begin. At first glance, This looks like a primitive agricultural method, but in reality, it is a calculated engineering defense. From above, the land looks like a gigantic checkerboard of golden squares stretching all the way to the horizon. It gets more complex further on. Once the grid is in place, mechanical augers and planting machines move in to drill small holes at the center of each square. These machines prepare the soil for drought-resistant species such as saxol, desert poplar, and red willow. Seedlings, carefully nurtured in nurseries, are transplanted into each hole at the center of the straw grid. One can notice how workers add a measured amount of water and compact the soil around the base to ensure the roots make full contact with the moist layer beneath. Therefore, the straw layer shields these fragile roots from the scorching sun and prevents the fine sand from eroding before the plant can take hold. As weeks go by, the straw gradually decomposes through the action of wind, animal activity, and microorganisms. The material slowly turns into an organic blanket rich in nutrients that feeds the developing root systems. This natural fertilizer helps the roots extend deeper into the stable soil layers below, anchoring the dunes permanently against the wind. The once barren sand slowly evolves into a living network of vegetation. Two distinct strategies converge to combat the relentless advance of the desert. African agricultural methods merge with Chinese engineering scale to create a unified front against soil degradation. Why is this specific collaboration so critical? The harsh climate breaks individual defenses easily. Collaboration ensures that traditional knowledge is reinforced by industrial capacity to hold the terrain. At first glance, the stabilization looks complete, but in reality, it requires continuous monitoring of the soil composition. One can notice how the sand stops moving under the weight of new vegetation. But this is just the beginning. The land transitions into a stable cycle of recovery.